Hello everyone, welcome to Score Booster series for GATE 2026. Today's subject is power electronics. In this session, we are going to discuss numerical answer type and multiple select type questions. Right? Here I have collected few questions from previous year GATE examination and few are the new questions to you. Right? Yeah. Myself, Rajendra. I have done M.Tech from Indian Institute of Science, Bangalore. I was All India 7th ranker in the GATE examination and currently working as a faculty member at ACE Engineering Academy, Hyderabad. So let us start with the questions. So in power electronics, the first chapter is the power semiconductor devices. As long as GATE examination is considered, from chapter number 1, these are the important topics. Repeatedly they have asked the questions on these topics. The first topic is a transition state, energy and a power loss in a practical switch. Right? That is ESW and PSW. We know in transition state there are two types, turn on transition and turn off transition. Okay? Right. During our classroom sessions also we discussed this bit. Second important topic is a conduction state power loss, that is P average, average power loss during on state in a switch. Next, some questions on a composite switches, like operating points of a composite switch. Repeatedly they ask the questions on a GATE examinations. And how to find the minimum width of the gate signal given the latching current value. Alright, so these are the important bits actually. Repeatedly they ask the questions on these bits. Right. Let us discuss now questions from chapter number 1, power semiconductor devices. Yeah, this question. Yeah, consider these as, instead of 1, 2, 3, 4, let us consider these as A, B, C, D. A, B, C and D. Right, A, B, C, D. So this question is now multiple select question. Yeah, let us discuss. Figure shows 4 electronic switches 1, 2, 3 and 4. Which of the switches can block voltages of either polarity applied between terminals A and B when the active device is in the off state? Yes. You can post your answers in a chat box. We will discuss the solutions. Yes, the session will be interactive session. You can post your answers in a chat box. I will give you 2 to 3 minutes. You can try and then we will discuss the solution. Right? Yeah. Yes. Yeah. B and C. Very good. Yeah, some are saying B and C, some are saying only B. Okay, let us discuss. So, from this given question, what is they are asking? The switch is required to block voltages of either polarity. Voltages of either polarity means forward voltage as well as reverse voltage blocking. Means a bipolar device. Out of these 4, which are the bipolar devices they are asking? Bipolar switches. Right. So here switch number 1, what is happening in switch number 1? If you check, when I maintain forward voltage like here plus and here minus, this is my composite switch. In this composite switch, IGBT is active device. Alright, IGBT is active device. When this device is in an off state, current will not flow from A to B through IGBT or through diode, because diode will not allow reverse current. Means this switch is having a forward voltage blocking capacity. But what will happen if I maintain the reverse voltage? If I maintain reverse voltage, then suppose here it is plus and here it is minus. Then this diode will immediately start conduction. When diode starts conduction means current will flow. Current flowing means your switch is unable to block the applied reverse voltage. Right? So when I apply reverse voltage independent of status of IGBT, this diode will immediately start conduction. So this switch is only unipolar switch. This switch cannot block a reverse voltage. So this switch is not fulfilling our requirement. What about the second switch? IGBT and diode in a series. If I apply forward voltage like plus here, minus here, when active device is in off state, active device is IGBT. When this is in a off state, means here it is open circuit. No current will be flowing from A to B. Alright. So current is not flowing from A to B. The meaning is my switch is having the ability to block the forward voltage. Similarly, if I check the reverse voltage, if I check for the reverse voltage, yes, here it is plus and here it is minus. What will happen? If I apply reverse voltage, then this battery, reverse voltage means I am connecting supply between terminal A and B. With the positive plate is connected to the terminal A, negative is connected to the positive is connected to terminal B, negative is connected to terminal A. So my battery will try to circulate current in a reverse direction, that is upward direction, but diode will not allow the current now. So reverse current is not flowing. The meaning is my composite switch is having the ability to block the reverse voltage. So this is a bipolar device. What about SCR? SCR is not a composite switch. It is a simple single device. And we know SCR is a bipolar device now. It can block high forward voltage as well as high reverse voltage. So this is also having the bipolar. This is also having the forward as well as reverse voltage blocking capacity. But what about this case? Here, when I apply forward voltage and if SCR is in an off state, then current will not flow through this branch as well as current will not flow through diode. Means when SCR is in an off state and if I apply the forward voltage, the current is not flowing. The meaning is my switch is blocking the applied forward voltage. But if I apply the reverse voltage, what will happen? If I apply reverse voltage, yes, like here plus and here minus, then this diode will immediately start conduction. Diode start conduction means your current will flow like this, right? Current is flowing means your switch is unable to block the reverse voltage. So this is your unipolar device. So bipolar only two, we are having a B and C, right? B and C. So correct answer is here B and C. B and C, right? Multiple select question. Recently also check GATE 22 or GATE 23. One multiple select question they asked based on this composite switch. Okay. So till now in power electronics, as long as multiple select questions are considered, they have asked the questions only on a composite switch operating points. Okay, right. Yes, next. Yeah. Let us discuss this question. A steady DC current of 100 ampere is flowing through a power module S, D. This is a power module S, D, right? Next, as shown in the figure A, the VI characteristic of the IGBT, this is VI characteristic of IGBT, and the diode D are shown in figure B and C respectively. This is the VI characteristic of diode, this is the VI characteristic of IGBT they have given. The conduction power loss in the power module SD in watts is. They are asking conduction power loss, that is P average, and they are saying which current is flowing, 100 ampere current. And check here, they have given the direction of the current also, 100 ampere. Come on, you can post your answers in a chat box, right? Please. What is the conduction state power loss here? Current direction they have given, VI characteristic of IGBT and your diode also given. Then what is the conduction power loss? Yes, can anyone? Yes, okay. Tell me, if current is flowing in a upward direction, current is flowing in a upward direction, so this current will flow through which device, whether through IGBT or whether through diode? Obviously current will flow through diode na. IGBT is a unidirectional device, right? That is not having a reverse current carrying capacity. but because of this diode, now this current is now flowing in this direction. So current direction upward means this diode will be in a conduction mode. So now for this power module, when current is 100 ampere DC and it is flowing in upward direction, only diode will be in a conduction mode. So here we need to find the conduction power loss in case of diode, that is P average. We know diode during on state belongs to which modeling? Third modeling na? Vt in series with the Ron, right? So diode during on state is represented with the Vt in series with the Ron. So this is your Vt and here it is Ron, right? Vt in series with Ron. Next, now what is Vt and what is Ron? That we need to find from this given plot. They have given it is a Vi characteristic of a diode. So can I say that from this Vi characteristic, this voltage indicates the Vt, minimum voltage required. So what is that Vt value? 0.7. So in this case Vt is 0.7. Vt is equal to 0.7. And what is Ron? Ron is nothing but slope, 1 by slope na. But here they have given dV by di. dV by di means it is a ratio of voltage to current for this curve. So it is a 0.01 ohm, means Ron is nothing but 0.01 ohm, right? So this is my Ron. Ron is 0.01 ohm. Now Vt and Ron we got from this plot, alright. Now tell me, if a constant current of 100 ampere flows through this diode, then what is the P average? We know in case of diode, P average, or in third piecewise modeling, P average equal to Vt into I average plus I RMS square into Ron. I RMS square into Ron, right? I RMS square into Ron. Now put the value here. Vt is a 0.7 into I average for a DC current of 100 ampere DC current, that is constant current. What is the average value, RMS value? Same 100 ampere, right? So here I average is 100 plus I RMS square for DC current, average value RMS value is equal to its amplitude. So RMS square means 100 square into Ron. Ron is 0.01, right? This will give you the P average, alright. So if you check, it will come like 170 watts, right? 170 watts, fine. Yes. Next, yeah, let us discuss this question. An SCR having a turn on time of 5 microseconds, latching current of 50 milliampere, holding current of 40 milliampere, is triggered by a short duration pulse and is used in the circuit shown in figure. The minimum pulse width required to turn on the SCR will be in microsecond. So they are asking what is the minimum width of the pulse width to turn on the SCR. Yes. How to find these type of questions we discussed during our classroom sessions also. Minimum width of the gate signal required. Yeah. So here this is my SCR. Consider this current is I, this current as I1, this current as I2, alright. Next, I need to maintain the gate signal till my SCR current reaches which value? Latching current value, right. So simply follow the procedure. For t less than 0, for t less than 0, SCR is in a off state. Gate signal is not applied to SCR, so my SCR is in a off state. At t equal to 0, we are applying gate pulse to SCR. At t equal to 0, gate pulse applied to SCR. T equal to 0, gate pulse is applied to SCR. So therefore my SCR will turn on. At t equal to 0, SCR will turn on, alright. Yes. Now when SCR turns on at t equal to 0, what is the status of inductor? Before t equal to 0, SCR was in a off state, so current flowing through the inductor, it was a 0 na. When SCR off state means open circuit, no current will be flowing in circuit. So I1, I2 both will be 0. Even I is also equal to 0 before t equal to 0 I am saying. At t equal to 0, when you apply get pulse to SCR, first this inductor will behave as an open circuit. Inductor opposes the sudden change in current, right? So at t equal to 0, when SCR turn on, then my I1 will remain equal to 0 ampere because inductor will act as an open circuit. And what is I2? I2 equal to 100 upon 5k na? Check, when SCR on state at t equal to 0, this 100 volt will appear across this branch. So I2 equal to 100 upon 5000. 100 upon 5000, which is equal to 20 milliampere, right? 20 milliampere. And what is current in a SCR? Current in a SCR at t equal to 0 is I1 plus I2. When this is in on state, I equal to I1 plus I2, right? So at t equal to 0, I is equal to I1 plus I2, which is equal to 20 milliampere, right? 20 milliampere. This is the current flow through the SCR at t equal to 0, right? T equal to 0. Now for t greater than 0, I am saying for t greater than 0, I am not saying for t equal to infinity. T greater than 0 means for finite time. For t greater than 0, what will happen? SCR will be in on state. Resistor will act as resistor, inductor will act as an inductor. So my circuit is like this: 100 volt, SCR is in on state, R, inductor, and this is the resistor. Yes, 100 volt, SCR, this current is I, here it is I1, here it is I2. It is 5 kilo ohm resistor and 20 ohm and 0.5 handle. Yes. Now, what is the expression for I1? For t greater than 0, if you check this branch, across this branch DC voltage is 100 volt present. So when DC voltage source is connected across RL branch, what is the expression for current? Yes, expression for current is equal to voltage upon branch resistance, that is 100 upon 20 into 1 minus e to the power minus t by tau, RL branch. So time constant tau is L by R, right? Yes, so it is e to the power minus 20 into t upon 0.5. So it is equal to 5 into 1 minus e to the power minus 40 into t. This is my current I1. Current I1, right? And what is I2? I2 is straightforward, 100 by 5000. I2 equal to 100 by 5000, which is equal to same 20 milliampere. And what is current from the SCR? I is equal to I1 plus I2, which is equal to 5 into 1 minus e to the power minus 40t plus I2 is 20 milliampere means 0.02 ampere, right? So from this I can write it as 5 plus 0.02 means 5.02 minus 5 into e to the power minus 40t. This is current in a SCR, right? Now from this current expression, we need to draw the current waveform for the current I, and I need to maintain the gate signal till my SCR current reaches which value? Latching current value. Yes, check here, put t equal to 0, e to the power 0 will be 1, so 5.02 minus 5 means current will be at t equal to 0, current will be at 20 milliampere, that is 0.02, right? After that, as time increases, this term will decrease, so this difference will increase, current will increase. At t equal to infinity, put here infinity, this term will become 0, so current is 5.02. So your current will be exponentially increasing and reaching to steady value of 5.02, right? When current increases from 20 milliampere to 5.02, somewhere it will cross to which value? Latching current, right? And I need to maintain the gate signal till my SCR current reaches latching current value. So this is my gate signal now. Pulse width is now TP. How to find this TP now? In this expression, simply put at T equal to TP, I is equal to IL, right? In this expression, replace T with TP and I with IL. So I can write here. Now IL equal to 5.02 minus 5 into e to the power minus 40 into TP. That is, at T equal to TP, I is equal to IL, right? At T equal to TP, I equal to IL. Now IL they have given, you can put here IL, which is equal to 50 milliampere. 50 into 10 to the power minus 3 is equal to 5.02 minus 5 into e to the power minus 40 into TP, right? So one equation, one unknown. You can simplify this, right? Yeah. So these type of questions also you can expect, right? Be careful. Not like only one loop question, you will be having like two parallel branches also. Okay, right? Repeatedly they ask the questions. Yes. Fine. Yeah, let's move towards the next question. Yes, yeah, let us discuss this question. A thyristor T in the figure below is initially off and is triggered with a single pulse of width 10 microsecond. So thyristor is triggered with a pulse, gate pulse of width 10 microsecond. TP given. It is given that L equal to 100 by pi microhenry and C is 100 by pi microfarad. Assuming latching and holding currents of the thyristor are both 0, holding current, latching current, both they are saying 0, and the initial charge on the capacitor is 0, then thyristor conducts for. Yes, now here check, latching current, holding current, they are saying 0, and thyristor is triggered with a gate pulse of 10 microsecond, right? And here turn on time, T on, they have not mentioned, correct? So here simply we need to assume when I apply the gate pulse, my SCR is now in a conduction mode. SCR is in a conduction mode, right? And after that, they are asking for how much time this SCR will be in a conduction mode, they are asking. Simply here, suppose at T equal to 0, I applied the gate pulse to SCR. So my SCR will now start conduction. And for T greater than 0, what will happen? Supply voltage, SCR will be now on state, inductor will act as inductor, capacitor will act as a capacitor. So my circuit will be like this for T greater than 0. For T greater than 0, circuit is like this. 15 volt, SCR is in a on state, inductor will act as inductor, capacitor will act as a capacitor. This voltage is 15 volt. Yes, SCR, inductor. Yes, let me write it as L only, C only. And suppose take this as Vs. Vs equal to 15 volt. Current in a circuit is I. We need to now find the expression for current in a circuit. From that we can get idea for how much time my SCR will be in a conduction mode. Here simply apply KVL to the loop. KVL to loop. Yes, I will be getting plus 15 or plus Vs. Let me write in terms of Vs. Plus Vs minus L into di by dt minus 1 by C integration of I into dt equal to 0 na. Now shift these terms to the right hand side. So Vs equal to L into di by dt plus 1 by C integration I into dt. Now take Laplace transform on both sides. Taking Laplace transform. Taking Laplace transform on both sides. Both sides, right? So I'll be getting it as Vs by S equal to Ls into I of S plus 1 by Cs into I of S, right? From this it is Vs by S is equal to Ls plus 1 by Cs into I of S, right? Take this multiplication, so I can write it as Vs by S equal to LCS square plus 1 upon Cs into I of S. S will get cancel out, right? Again Vs equal to, take LC common from this numerator, take LC common, so that coefficient of S square will become equal to 1. So it is LC into S square plus 1 by LC upon this C as it is into I of S. So C cancel out, right? So from this what I can write, I of S equal to Vs by L into excuse me, 1 upon S square plus 1 by LC, right? Now we need to rearrange this term. Check, this is like your tank circuit again. In DC to DC converter, before your thyristor commutative choppers, we discussed the tank circuit. So like a tank circuit, we are getting here current expression now. What I need to do? I need to multiply numerator denominator with 1 by root LC, so that this term will become Laplace transform of some time domain function. So I can write it as I of S equal to Vs by L into 1 by root LC upon S square plus 1 by LC into root LC, right? Check, root LC cancel out, again the same term, right? Now here, yes, this 1 by root LC I am going to represent it as a omega 0. So what I can write, I of S equal to, yes, check here, Vs by L and this root LC. So out of that 1 root L cancel out. So in the denominator we will be getting Vs into under root C by L total, right? Root L, this root L will get cancelled out, only root L will remain in denominator. So it is Vs under root C by L into omega 0 upon S square plus omega 0 square, where omega 0 equal to 1 by root LC, omega 0 equal to 1 by root LC, right? Now I can directly take the inverse Laplace transform. Taking inverse Laplace transform, what I can get, I equal to Vs under root C by L into sine of omega 0 t. This is my current expression. This is my current expression, right? So what will happen here? My current nature in the circuit is a sinusoidal. Current in a circuit is a sinusoidal nature. So my current is like this. This is time t 0. I'll be getting this type of current nature. This time is pi by omega 0. Check, pi by omega 0. If I put t equal to pi by omega 0, that will become sin pi. Sin pi is 0, so you'll be getting 1/2 cycle sinusoidal. It is sinusoidal, right? Yeah. So check here, at pi by omega 0, my current will become 0. So at this point your SR will turn off, because as per this expression, after this point my current will try to go in a negative value na. Sinusoidal means after half cycle current will try to go in negative value. Negative value means my current will try to reverse, but whether my SR will allow reverse current? No. So here my SR will stop conduction, right? So they are asking what is the thyristor, both 0, okay, 0. Thyristor conducts for, so thyristor will conduct only for t equal to pi by omega 0. This is my thyristor will be in on state during. So conduction time of thyristor, therefore conduction time of SCR equal to pi by omega 0, but omega 0 is 1 by root LC, so that is nothing but pi upon 1 by root LC. So I can write it as a pi into root LC. Now L and C value they have given, you can simply put here, you can get answer, right? Yes. So please understand here, this is one important question, right? You need to understand, you need to find the current expression, or simply you can take this reference as like a reference of your tank circuit. In tank circuit also we got this type of expression. So, right, if you get this reference, means directly you can understand the nature of current will be like a sinusoidal type of the nature. Okay, right? Yeah. Next, yeah. Let us now discuss questions from AC to DC converter, right? So before that, which are the important topics from AC to DC converter? Here, single phase, half wave, controlled and uncontrolled rectifier. These circuits are important, but only repeatedly they ask the questions on R load, that is resistive load, and a purely inductive load, right? Single phase, half wave rectifier, uncontrolled and controlled, purely resistive load, purely inductive load. These two are important, right? Next, single phase full converter. Full converter means bridge rectifier, where 4 SCRs were using. Important one, loads, important loads are R load, RL load and RLE load. But RL and RLE only highly inductive load were having, right? If you check your operation of the circuit for RL as well as for RLE, operation waveforms are same, only one expression is different, that is I0 average, alright? So these are important. In 3-phase rectifiers, 3-phase half wave rectifier, 3-phase full wave rectifier, full wave, that is a full converter, 6 thyristors were connecting. In that, highly inductive load, RL and RLE, these are important. Repeatedly they ask the questions. And input power factor for highly inductive load. We discussed this, right? Input power factor for highly inductive, where we are finding the distortion factor, displacement power factor, right? Right. So they have asked the questions on these bits. Okay. Repeatedly I am saying. Yeah. It is not like your other loads are not important. Comparatively on RE load, they have asked the less questions. RE, that is battery charging circuit, comparatively less questions. Maximum questions on these type of loads only. Okay. So these are very important circuits. Yeah. Let us now discuss the questions from rectifiers. A half controlled single phase bridge rectifier is supplying an RL load. It is operated at a firing angle 60 degree and the load current is continuous. Load current continuous means continuous conduction. The fraction of the cycle that the freewheeling diode conducts is, come on, what is the fraction of cycle the freewheeling diode will conduct? Can anyone? Yes, you can post your answers in chat box. Yes guys, you can post your answers in chat box. Yes, 1/3. Good. Huh. So here they have given single phase bridge rectifier, means 4 thyristors, and load is a highly inductive RL load. RL load means by default you are required to assume it as a highly inductive, because in highly inductive load only we are having in syllabus. Next, the fraction of cycle that the freewheeling diode conducts. Freewheeling diode conducts means it is load is now RLFD, RL load with the freewheeling diode, RL load with the freewheeling diode, RL load with the freewheeling diode, right? Now for this, if you recall the conduction sequence of devices, let me draw the waveform of V0 and in that we can write the conduction sequence. Yes, 0 to alpha, alpha to pi, pi to pi plus alpha and 2 pi. Yes, here 0 to alpha which device conduct? Freewheeling diode. Alpha to pi, thyristor T1 T2, right? Check RL load freewheeling diode single phase full converter. We are getting this type of waveform. First T1 T2, then freewheeling diode, then T3, T4, and again freewheeling diode, right? This is my conduction sequence. Now over 0 to 2 pi, my freewheeling diode conduct here and here na. So here my total conduction angle of freewheeling diode is 2 alpha. Conduction angle of freewheeling diode is 2 alpha out of how much angle? 2 pi. 2 alpha by 2 pi, that is nothing but alpha by pi. Fraction they are asking na. So fraction is alpha by pi, but alpha is 60 degree, means pi by 3 radian upon pi, that is equal to 1 by 3. So your answer is 1 by 3. Alright, that is 0.333, etc. So it is like 2 alpha upon 2 pi, or simply you can take alpha upon pi also, same you will be getting 1 by 3 only, right? Simple question, right? 1 by 3. Yeah. A 3-phase diode bridge rectifier is feeding a constant DC current. Diode bridge rectifier they are saying, 3-phase diode bridge. 3-phase diode bridge rectifier, yes, feeding a constant DC current of 100 ampere, that is load is a highly inductive, to a highly inductive load. If 3-phase 415 volt 50 Hz AC source is supplying to this bridge rectifier, then the RMS value of the current in each diode in ampere is, they are asking ID RMS value of a diode current. Come on, tell me. Thyristor rectifier highly inductive load, diode rectifier highly inductive load. What is the difference? If I put alpha equal to 0 degree in Thyristor rectifier, I will get diode rectifier na. Waveform is like a diode rectifier, right? So here, if you recall, in case of Thyristor rectifier, we have drawn the waveform of Thyristor current IT1. How is the Thyristor T1 current waveform? Each Thyristor conducts for 120 degree. Thyristor pair conducts for 60 degree, but Thyristor conducts for 120. So if you recall, my Thyristor T1 conducts from pi by 3 plus alpha till pi plus alpha out of 2 pi. Highly inductive load. And during this interval, which current flows through Thyristor T1? Load current, right? Load current flows through the Thyristor T1. So this is my Thyristor current waveform. Now if I want to draw the diode current waveform, what will be the change? If I want to draw the diode current waveform, because here they are talking about the diode rectifier. Yes. In case of diode rectifier, alpha will remain 0 na. So therefore I can say that my diode will conduct from pi by 3 till pi. It is like from pi by 3 till pi my diode conduct out of 2 pi. And which current flows through diode? Again load current. Again load current na. So this is my I0 now. So my diode current waveform is now pulsating in nature. Now we can find the ID RMS, right? What is ID RMS? ID RMS equal to, yes, amplitude square function duration. Function duration is 2 pi by 3 upon periodicity, that is 2 pi to the power 1 by 2, that is equal to I0 by root 3. I0 is 100, so you will get it as 100 by root 3 ampere, right? You can write that in fraction, okay, right? So check, yes, divided by root 3, nice, fine. Okay, so here you need to recall, we have drawn everything, Thyristor current waveform, supply phase current waveform also we have drawn, alright. Next, now let us discuss this question. This is actually multiple select question. In the circuit shown, the diodes are ideal. The inductance is small, source inductance this is, at source side it is corrected. So this is your source inductance. And I0 is a non-zero. Which one of the following statement is true? D1 conducts for greater than 180, D2 conducts for 180, D1 conducts for 180, D2 conducts for more than 180. Come on. You can post your answers in chat box. Load current is constant here. In the load branch, they have shown current source. The meaning is my load current is a constant, right? Yes. Out of these four, which are the correct options? This is a multiple select question. More than one option will be correct. Okay, only A and B, check once. Yes. Okay, only A, huh? Let us check. Here, this is my source inductance present, right? If you want load current now here constant, I want load current here constant. What will happen here? First tell me without source inductance. Without source inductance, how will be my waveform of diode D1 current and diode D2 current? Without source inductance, my diode, suppose let me consider this current as ID1 and suppose this current is ID2, right? Yes. Now, without source inductance, how will be my ID1 and ID2? Without LS, yes, how will be ID1 and ID2? Without LS, what will happen? 0 to pi my diode D1 conduct na, and pi to 2 pi diode D2 conduct. Alright. So here 0 to pi my ID1 equal to I0. Without LS, my ID1 is this type of waveform. Right? Because 0 to pi supply voltage positive, diode D1 conduct, current will flow like this. ID1 equal to I0. Alright. Next. And when supply voltage negative, that is pi to 2 pi, then this diode will turn off. Load inductor will be discharging like this only. Right. So ID2 will be I0 now. During pi to 2 pi, my ID2 will remain I0. This is my load ID2 waveform. This is like pi and this is 2 pi. Now tell me, this is without LS. If source inductor is present, what will be the modification in ID1, ID2? Tell me, if source inductor is present, whether this source inductor will allow my diode D1 current to suddenly change from 0 to I0? No. So therefore my ID1 will be slowly changing, like 0 to mu, mu means overlap angle. During 0 to mu, my ID1 will be slowly increasing. And at pi, ID1 is suddenly dropping to 0. If source inductor is present, whether this source inductor will allow this ID1 to suddenly drop to 0 at omega t equal to pi? No. So when LS is present, my ID1 will be at pi, it will be slowly decreasing. So my ID1 waveform, when LS is present, yes, I am drawing here, with LS, yes, my ID1 waveform will be like this: 0, mu, pi and pi plus mu. Yes, let me take like this. Pi, this is like pi plus mu, and here it is like 2 pi. So 0 to mu, my ID1 will be increasing nature. After that it is a constant I0 till pi, and after that it will be decreasing nature. After that decreasing nature, and then it will be 0, right? This is my ID1 waveform. If this is ID1 waveform, how will be ID2 waveform? How will be ID2 waveform? Zero mu pi plus mu 2 pi, right? Tell me how will be the ID2 waveform. Check here. During 0 to mu, diode D1 conduct na, 0 to mu diode D1 conduct. So ID1 is increasing means what? ID1 non-zero. So D1 will be in a conduction mode. But during 0 to mu, my ID1 is less than I0 na? ID1 is less than I0 here. But my load demands constant current na? Load will demand constant current. So what is happening during that interval? Load will not accept the current less than I0. Load will not accept the current, load will not accept the current less than I0. So my ID2 waveform will be this type nature. Check. This waveform is continuous cycle waveform I am drawing. This point is I0. Means during 0 to mu I am saying that diode D1 as well as diode D2 both will be in a conduction mode. The thing is ID1 is a less than I0, means supply is unable to fulfill the requirement of load. So whatever the difference current is there, listen the statement carefully. Whatever the difference current is there difference between I0 and ID1, that current your load inductor will be discharging through diode D2. So my ID2 will be this type of nature. If I add these two, I will get I0. Now tell me, from mu till pi, ID1 is I0, so ID2 will be 0. ID2 will be 0. At this instant, my diode D2 current becomes 0, so D2 will turn off now here. After that, it will be in a off state, right? Now after pi, what is happening? Again, ID1 is decreasing. So my ID2 will, now it will be increasing this type nature. And after that, it will be constant. And after 2 pi, again this same pulse will come here, right? So please understand here, if I add ID1 and ID2, I will get I0. Please understand, okay? So without LS, it is very simple. But because of LS, what will happen? My diode D1 will not suddenly rise or suddenly fall. Due to that, my diode D1 current nature is like this. And if D1 current nature is like this, because of that, my D2 current nature also it will change, right? Because load branch will not accept the current less than I0, okay, right? So here tell me diode D1 conduction and diode D2 conduction. What is D1 conduction? D1 conduct from 0 to pi plus mu na, so conduction angle is greater than 180. For D2, check, over 0 to 2 pi, my D2 conducts for how much angle? It is like from pi till 2 pi it conducts. At the same time this mu also na, so D2 also conducts for pi plus mu, D1 also conducts for pi plus mu. So both will be conduction for angle greater than 180 degree. So correct answer is option D1 conducts for 180, D1 conducts for greater than 180, D2 also conducts for greater than 180 degree. Alright, so correct answers are A and D. A and D are correct answers, right? Yes. Please understand this, without LS and with LS actually what is happening, right? Next, let's discuss this question. Simple question. A single phase fully controlled converter bridge is used for electrical braking of a separately excited DC motor. The DC motor load is represented by an equivalent circuit as shown in the figure. Okay, they have given this. It is an inverter mode operation. Alright. Now here, assume that the load inductance is sufficient to ensure the continuous and ripple free load current, right? The firing angle of the bridge for a load current of I0 is 10 ampere will be. They are asking the alpha value they are asking. Load current is constant to 10 ampere. Okay, right. Now how to find the alpha value? Check, load current given 10 ampere. So here current is 10 ampere. Right. From this, can we find V0 average? This is your V0. First find V0 average. right? We can write here V0 average equal to I0 they have given na. What is I0 given? I0 equal to V0 average plus E by R. Inverter mode operation, EMF polarity reversed, so that's why it will become plus E by R, right? Now from this, what is V0 average? I0 into R minus E na, I0 into R minus E. Now I0 is 10 ampere, R is 2 ohm, minus E is a 150. From this you can get it as a minus 130 volt. This is V0 average. Now what is the expression for V0 average? For single phase full converter highly inductive load, expression for V0 average is 2 Vm by pi into cos alpha. Now here write 2 Vm by pi into cos alpha is equal to minus 130 na, minus 130. Now put the value, 2 into Vm is 230 root 2 upon pi into cos of alpha is equal to minus 130. So from this you can get alpha, right? Check, you will get this alpha greater than 90 degree because inverter mode operation, right? You can check this, right? Yeah, it is 128 point something. Yeah, someone messaged, right? Right. Okay. Next. Yes. Yeah, this question is from GATE 2019. A single phase fully controlled Thyristor converter is used to obtain an average voltage of 180 volt. They are saying single phase fully controlled means full converter. Single phase full converter and V0 average is 180 volt. V0 average 180 volt with a 10 ampere constant current, means load current is a constant. It is fed from a single phase AC supply voltage given. Neglect the source impedance. The power factor of AC mains is, that is input power factor they are asking. Single phase full converter highly inductive load, what is the input power factor? Input power factor equal to 0.9 into cos alpha na, 0.9 into cos alpha. Now here first we need to find the alpha. For finding alpha, they have given here V0 average. V0 average is equal to 2 Vm by pi into cos alpha na, 2 Vm by pi into cos alpha, right? So here V0 average is a 180, it is equal to 2 into Vm, peak value of supply 230 into root 2 upon pi into cos alpha. From this you will get cos alpha. Put that cos alpha directly, you will get input power factor. Alright? Yes. A simply expression based question, that's it. Yes. A fully controlled 3-phase bridge converter is working from a 415 volt 50 Hz AC supply. It is supplying constant current of 100 ampere. I have taken highly inductive load numericals only here, because maximum they ask the questions on highly inductive load, right? Yeah. AC supply, it is supplying constant current of 100 ampere at 400 volt to a DC load. Assume large inductive smoothing and neglect overlap. The RMS value of AC line current in amperes. They are asking RMS value of AC line current, that is IRMS. They are asking IRMS. Yes. Check the data whether they have given the load current. Yes, constant load current given na 100 ampere. For 3-phase full converter highly inductive load, what is the RMS value of phase current? Supply star connected. So in star connection, line current, phase current both are same. Okay. So here line current means, as per our notation, we use it as a IA. So it is IRMS they are asking. What is the IRMS expression we have written? It is under root 2 by 3 into I0. So it is under root 2 by 3 into I0. I0 is 100. So simple question, that will give the IRMS. All right. But this type of question they have asked. So IRMS expression important. IT average, IT RMS expressions are important for specifically 3-phase. Okay, right, and highly inductive load. Yes, next. This question is from gate 22 based on a single phase semi-converter. Yes. For the ideal AC to DC rectifier circuit shown in the figure given below, the load current magnitude is 15 ampere, load current constant 15 ampere, and is ripple free. The thyristor are fired with a delay angle of 45 degree alpha given. The amplitude of fundamental component of the source current IS1 peak amplitude na. So IS1 peak they are asking, peak value of fundamental component of source current. Check while discussing the input power factor for highly inductive load. For the supply current, we have derived the Fourier expression na, Fourier expression of supply current. From that we can find IS1 peak. What is IS1 peak? Yes, IS1 peak is equal to, yes, it is 4I0 upon pi into cos of semi-converter alpha by 2 na, 4I0 by pi into cos of alpha by 2. Yes. So this is my expression. So you can put the values. 4 into I0 is 15 upon pi into cos of alpha by 2. Alpha is 45. So 45 by 2. Yes, you can get it, huh? Right. Yes, it is 17.6. Fine. All right. And now let us discuss few questions. Yeah, few 10 minutes I will take more. Let us discuss a few questions related to the DC to AC converter. Now, DC to AC converter, power semiconductor devices, and DC to DC converter. These 3 chapters are comparatively easy to understand, comparatively less contents, and weightage is also comparatively equal weightage. Okay, so don't think like a rectifier is a vast chapter, it is a big chapter, so more weightage will be for rectifier. No, it is like for 4 chapters, it is more or less somewhat equal weightage. Okay, so you should first prepare like these 3 chapters: power semiconductor devices, DC to DC converter, and DC to AC converter. Okay, and then go for the rectifiers. Right. So in inverters, that is DC to AC converters, important topics are single phase inverters, in that R load and purely inductive load. As such, in gate and in ESC prelims, they have not asked the questions on REL load, right? They have asked the questions only on purely resistive and purely inductive. All right. Next is pulse width modulation techniques. In that, single PWM and sinusoidal PWM, these are very, very important. Repeatedly they ask the questions on this. On multiple PWM, comparatively very less questions you will find. Okay, so these 4 are important, right? On 3-phase inverters also comparatively less questions they have asked, right? And more questions on this chapter they have asked based on the Fourier series expression of output voltage waveform, right? Yeah, let's discuss this question. In the converter circuit shown below, the switches are controlled such that the load voltage V0 of t is a 400 Hz. So frequency given 400 Hz square wave. The RMS value of fundamental component of V0 of t in volts is, yes, they are asking fundamental component of output voltage RMS value, means V0 1 RMS, V0 1 RMS. Yes, simple question. Full bridge inverter, supply voltage given, we can find now V0 1 RMS. What is V0 1 RMS expression? V0 1 RMS equal to full bridge inverter. So it is a 2√2 into Vs upon pi. We are having the 4 Vs by pi na, but that is the amplitude. And what is the RMS? Divided by √2. So 4 by √2 means 2√2. 2√2 into Vs by pi. So it is 2 root 2 into Vs is 220 upon pi, right? You can simplify this, you will get the answer, right? Yes, simple. Yeah, let us discuss this question. Yeah, this question is from GATE 2019. The output voltage of a single phase full bridge voltage source inverter is controlled by unipolar PWM with 1 pulse per half cycle. 1 pulse per half cycle means it is like your single PWM, right? For the fundamental RMS component of output voltage, fundamental RMS component means V01 RMS to be 75% of DC voltage. So V01 RMS is 75% of input voltage. The required pulse width in degree is, yes, will you try? Please check once, try to simplify this question. Yes, 1 pulse per half cycle means single PWM, right? So there, here we can simplify this with a single PWM. Single PWM. It is given that V01 RMS is equal to 75% of DC voltage, that is 0.75 into supply voltage Vs. You can write Vs or you can write VDC also. VDC also doesn't matter. Now V01 RMS is for single PWM V01 RMS. It is not like square waveform. It is a single pulse width modulation. What is the V01 RMS? 2 root 2 upon pi into Vs into sine of pi by 2 into sine d na into sine of d is equal to 0.75 into Vs. Alright. Check. Vs will get cancelled out. And here sine pi by 2 is 1. One equation, one unknown. From this you can get d. Once you get d, you can get a duty cycle, right? Pulse width means not duty cycle. You can get that pulse width. Pulse width is 2d na, right? Yes. Yeah, approximately it is 113 na. Yes. So pulse width is a 2d is equal to approximately 113 degree. Yes, few students have submitted that. Yeah, d is a 56.41 na, correct. From this you will get d 56.41 and from d you can find the pulse width. In single PWM we are representing the pulse width with the 2d. Alright, pulse width with the 2d. Yeah, check, simple, hardly in 2 lines we can get the answer. Yes, check this question. Consider an ideal full bridge single phase DC to AC inverter with a DC bus voltage magnitude of 1000 volt. The inverter output voltage shown below, yes, that is square waveform, is obtained when diagonal switches of the inverter are switched with a 50% duty cycle, right? The inverter feeds the load with a sinusoidal current given I of t. So they have given the current expression ampere where omega is 2 pi by t. The active power in watts delivered to the load is, yes. Come on, try to simplify this question. Here they are saying load current is a pure sinusoidal. Now I have given you hint, load current is pure sinusoidal. So what will be your load power? Come on. If load current is a pure sinusoidal, what will be your load power? Load current is not having any harmonics. So your load power will be equal to only fundamental power, right? Only fundamental power. So how to find fundamental power? V01 RMS into current is now sinusoidal means it is only fundamental current. So V01 RMS into I01 RMS into cosine of angle between V01 and I01. Yes or no? Right? So now here current is sinusoidal. Load current is sinusoidal. Load current they have given is a sinusoidal. So therefore, what notation they have used? I of t. Okay. Therefore, I0 of t, which is equal to I of t, is equal to only I1 of t, or I can write I01 of t. Be careful. What I am saying, load current as per our notation, as per their notation, it is I of t. It is a sinusoidal, means it is having only fundamental component, only fundamental. Okay. So my I01 will be equal to this expression now, 10 into sine of omega t minus pi by 3. If load current is a pure sinusoidal, that is only fundamental component, so my load power will be equal to only fundamental power, right? So for fundamental power we require V01 RMS. V01 RMS. How to find V01 RMS for this waveform? It is a square waveform. So we can write V01 RMS expression, right? They are talking about which inverter? Full bridge inverter. Okay. So it is a 4 by root 2, that is 2 root 2 Vs by pi. This is a fundamental. So it is 2 root 2. Supply voltage is 1000 upon pi. This will give you the V01 RMS. Okay, check this value once. Yes. And I can write P01. P01 equal to V01 RMS into I01 RMS into cos of phi 1, cosine of angle between V01 and I01. V01 RMS is 2 root 2 into 1000 upon pi into I01 RMS. I01 peak is 10, so it is 10 by root 2 into cos of angle will be pi by 3. This will give you the load power P0, which is equal to P01. All right. Yes. Okay. This will give the load power. Fine. Okay. ठीक है, right. Okay, so I think we are running out of time. ठीक है, so these are the few questions. Actually, I am having few more questions, but we are running out of time. Okay, so please go through this whatever the important points I told you from each chapter, which are the important bits. And one more thing, DC to DC converter we are not discussed here. In DC to DC converter, important topics are buck converter, boost converter, buck boost converter. Whatever the analysis we have done, that totally important. And in Thyristor commutated choppers, voltage commutated chopper. In Thyristor commutated choppers, only voltage commutated chopper is important. Current commutated chopper is not important because very less question they have asked. Okay. So in DC to DC converter, only 4 topics are important: buck boost converters, and your voltage commutated chopper. All right. Okay, so stop here. Thank you, thanks to all of you, and all the best for your examinations.